Look at locus of points, and all that we're looking at with locus of points is some kind of satisfaction to, a rule or equation or condition. And most of the time, these are going to be pretty straightforward. The locus of points is what x, y values will do such and such. So a classic one is you take 2 points that are not straight across from each other. Well, let's take 2 that are. Let's say we had -2, 0 and 4, 0. Okay, what locus of points are equidistant from those 2 points? Yeah, vertical line. Where would that vertical line be? All of these points x, y, where would they be? X equal to what? Well, you'd go 4 plus -2, which is 2, divided by 2, it'll be 1 at x equal 1. All of these will be equidistant between those 2 points, right? So we can do this with points that are not on a straight line, that they're even a little bit on a diagonal, and we can figure out what points those are for the same way. Pick a point x, y, and we want to do a distance from 1, 0 to that, and a distance from 5, 4 to that. And so those 2 distances, they just show the AP here. So we have x minus a -1 squared plus y minus 0 squared, x minus 5 squared plus y minus 4 squared. Those are just the distance formula. Distance 1, distance 2. You okay with that? So get used to squaring. With a lot of algebra this section here. X squared plus 2x plus 1 plus y squared. X squared minus 10x plus 25. Y squared minus 8x plus 16. Lose the x squareds. Lose the y squareds. Put the x's together. Put the y's together and the constants together. And you get 12x plus 8y equals 40, and you divide by 4, you get 3x plus 2y equal 10. Well, that is a line, and we would expect that line. The slope of that line, 2y equal to -3x plus 10, you get y is equal to -3/2 x plus 5. And this looks like about -3/2. The intercept would be 5. And what's interesting about the slope m equal to -3/2? What's interesting about that slope? Take a look at my picture. Perpendicular to what? Yeah, to AB. Let's see, what is the slope of 5, 4, -1, 0? Well, that slope is 4 minus 0 over 5 minus -1, which is 4. Ooh, this thing is not tracking. 4/6 or 2/3. Is that the perpendicular to -3/2? Yeah. Yeah, they would be, wouldn't they? If they're equidistant, those points? Yeah. All right, so now, at the bottom of this is a little, just looks like you're going to miss it, formula on the distance from a point to a line. Point to a line. And I wish I had this one last year for us. We could have used it. The proof for this one I'm going to go through. Super helpful to see where it comes from, but you don't have to prove this in the future, but I just want you to see how it is. I think the proof they have is missing a ton of stuff. So would you write this down with me? I'm going to be doing this with details, and it would really be great if you could do this with me. And fail safe. So here's what we have. We have this line, ax plus by plus c. Hi. Yep. Oh, he's not here. No. All right, so the line is ax plus by plus c equals 0. And then we have a point x1, y1, and I'm going to use a different color here. We're going to draw this through here so that the slopes are equal. So what's the slope of this line? Ooh, slopes. Back from break, it's tough. Slopes. You guys looking at me like, what do you mean slopes? Yeah, so what you would do is you'd go by is equal to negative ax minus c, right? And so y would be negative a over b, x minus c over a. Do you agree with that?
No.
Yeah. And so what would the y-intercept be? What's wrong? Oh, c over b, excuse me. Yeah, it does. I'm going to be, yeah, that's right. So then, but for the slope, this is just going to be your slope for this line, which is negative a over b. What would this slope be for this purple one? Same thing. Okay. And then we're going to be able to find eventually what we want to do is we want to describe these two lines here. We want to describe this vector. Oh, and I did say that word. Starts with a V, ends with an vector. This is a vector. You have this vector and this vector, and an angle in between we're going to call theta. We're going to be able to relate those two, but we need to define these two vectors first. So the first thing that we need to do is we need to define these 2 points, this point and this point. Well, this point is easy because what you're going to do is you're going to let y equal to 0. That's what the x-intercept is. So ax equal to negative c, x is just going to be negative c over a. So the coordinate for this point Q, they're calling, is negative c over a comma 0. You okay with that? Then s over here, a little trickier, but not that tough, is going to be, this one is going to be, you're going to set this thing equal to 0, a x plus b y1 x1 plus c equal to 0. And again, we're letting y equal to 0. So then what happens is that you're going to solve for this one, ax, oh, setting this equal to 0, and then you're going to solve for x again. So you get ax is equal to negative by, right? 1. Oh, I know what we did. Nope. That's not it. Step back just a little bit. This statement. This is saying that the slope of the green is equal to the slope of the purple. Do you agree with that? Nod your head if you agree with that. Okay, good. So if that's true, ax plus by equals ax1 plus by1. So now what we're going to do is we're going to say ax plus b times 0, because it's hitting the x-intercept, equal ax1 plus by1. Solving for x, you get ax1, or ax equal to ax1 plus by1, and now we're going to divide by a to get what x is. And there is your x, your y is 0. There you have it. You've got all of the vectors, all the points you need for the vectors now. You have this qs. Qs is going to be the change in y, or change in x over change in y. What's 0 minus 0? 0. So that's the change in y. The change in x is going to be a little bit of work. We're going to do ax1 plus by1 over a, and we're going to subtract c over A, negative C over A. Well, doesn't that just give us AX1 plus BY1 plus C all over A? Doesn't that give us that? So there's our QS. So we've got QS, that's blue. So hold on to that one. That's big. Then for this one, this one's a little trickier to get your vector, but not that tough. What was the slope of this line again? What was the slope? Thank you. Slope is negative A over B. Then what's the slope for this guy, this blue one? Slope perpendicular. B over A. And just a reminder, that's the change in Y over change in X. Okay? So now we're going to build a vector out of this. The X is now on the top, and the Y is on the bottom. This is where the X's are, and here's where the Y's are. I know that's a little confusing. You okay with that? Did I throw you off the track? And then K is the constant times A. K is the constant times B. We don't know what K is, but that's the distance they are between. So for the last part, once we have Q, R, and QS, and I'm going to highlight this one too. Here's QR, QS. Now we're going to take these vectors and we're going to remember a little bit of our vector training from a while back. Well, the relationship between these two is no big deal. That's just a cosine. Cosine of theta is going to be the magnitude of this, which is D, over the magnitude of AX. Well, we're just going to call this QS. It's the magnitude of this, magnitude of that. Adjacent over hypotenuse. Are we okay knowing that these are perpendicular? Then what they did is they rearranged them algebraically, solved for D, cosine times QS. And then I'm going to multiply by 1. It's the same as QS times the cosine. But then I'm going to multiply by QR and QR. That seems kind of wrong, doesn't it? Why make things messier and nastier? Well, we could, yeah, these are magnitudes. We are going to be able to find the magnitude of QR. Anybody know what the magnitude of this was? What was the magnitude of 1, 2? How did we find the magnitude of that? Yeah, it was the square root of 1 squared plus 2 squared. Good. What would this be if QR is KA and KB? What would that magnitude be? Square root of K squared, A squared, plus what? K squared, B squared. Good. But on the top, something weird happens. When I multiply QS, QR, cosine theta. Oh, this isn't bad. QS times QR and cosine theta. It's a long time ago in a mathematics class far, far away. Bing! You got it. Dot product. QS dot QR. That is the dot product. Remember when we found the area of a parallelogram and then an area of a triangle? We use this. It's a very obscure formula, but this is the definition of the magnitude of the dot product, and the magnitude of the dot product is this times that. Green times blue. So let's do it. I got to do it down below here. This is D again. Our distance is going to be green times blue. I got to look up there again. It's ax1 plus by1 plus c times, what's the green x part in the green? Ka, good. Plus the y in the QS is 0 times KB. Well, that's just 0, isn't it? All over the square root. I'm going to take out k squared, a squared plus b squared. And once I do that, this is gone, right? This 0 part. And then, did we? A squared plus b squared. Oh, wait a minute. Ka. No. Why did I have a... I did something wrong there. What did I do here? K times... I shouldn't have that extra a. Oh, I know what it was. I forgot to multiply by the 1 over a. Right? That's where the a went. Thanks for catching that. Good, good. So then, what's the square root of k squared? K. So my final distance formula is going to be k over k. Then it's going to be ax1 plus by1 plus c over square root of a squared plus b squared. Now, when you're looking at that, that is the formula for the distance from a point to a line. But here's what I want you to notice, the beauty of mathematics. Look at the distance from a point to a plane. What's the difference? What's the only difference between these two? What's that? You're essentially losing this whole z thing, and this d is really a c, isn't it? Well, I could have done that, but it really would have been kind of cheap mathematics. Yeah, it is. I could have done that, but this is, the constant is still a constant. Does that make sense? And so this is now 2D, which is what you guys are going to do next. So let's do it. Let's find some distances. Let's find a distance from a point to a line. Well, I'll show you. is you're going to, the distance, what you could do is you could say, okay, let's take this distance between x, y here, and this point 0, -3. Okay, that's going to be x minus 0 squared, y minus -3 squared. I guess we got this one. And then you do the other one, x minus 0 squared, y minus 3 squared. When you look at those, they don't simplify very well because this square root and this square root don't combine nicely. So you move them to the other side. Now square them. You're going to get 8 minus this square root. You're going to get 64. You're going to get this, but then you're going to get a middle term with a root in it. Move all these to one side. Cancel things out. Then move the square root over here so it's positive. Divide by 4. And then this thing, if you square both sides, gives you this nasty looking y squared. But here you're going to get 16 times these, and they simplified down all the way down to this 16x squared plus 7y squared equals 112. Now, if you divide by 112, you get this nice simplified thing. Tell me, what is x squared plus y squared equal to 4? What is that? Circle. What is x squared over 4 plus y squared over 4 equal to 1? Or, yeah, equal to 1. What's that? That's I didn't do anything different there. I just divide by 4, so it's still a circle. Okay. Then what's this? If I change this to an 8, now it's an ellipse. So with a circle, you're just dividing by the same thing. With an ellipse, they're different. They're called major and minor axes, which we'll look at in the next couple days. But that's the main thing. But if you ever want to make an ellipse, no kidding, you just take string longer than 2-point distances and just rub around it like kind of like the spirograph, and you got yourself an ellipse. Works every time. All right, go to exercise 2L. You guys are going to do some problems here, and then we should be able to go through the assignment.